Hello, this is Aguntuk Biswas, 18010001, and today I am going to be presenting on the topic Deep Learning for Snow Analysis. Throughout the years, machine learning techniques, especially those of deep learning, have been used in remote sensing projects that includes cloud segmentation, image classification, and facet labeling. Research has also shown potential in detecting snow coverage, presence, and boundaries. However, snow quantification still largely relies on expert opinions. Novel snow quantification method seeks to derive new formulas based on reflectivity and differential phases. Machine learning research has been largely focusing on identifying snow rather than quantifying snow. However, in recent years, researchers started to recognize the potential in forecasting and estimating snow water equivalent (SWE) in real time through machine learning techniques such as regression, trees, and feed-forward neural networks. Researchers also worked on explaining and drawing inferences from those machine learning models. Snow coverage predictions have largely relied on data collected through satellite images. The two major resources of remote sensing comes from Landsat and MODIS satellites. Landsat provides high resolution, around 30 meters data, but the data is recorded in low frequency, roughly around 16 days. MODIS provides daily low resolution images around 300 meters. A key measure of the amount of snow in a region is fractional snow cover, which is the fraction of the region that is covered in snow ranges from 0 to 1. The normalized difference snow index (NDSI) was used as the major indication of snow cover presence in comparison with fractional snow cover (FSC). In order to join the advantages from both data provider and produce high quality data samples, a new method is in modeling snow coverage through machine learning techniques such as multi-layer perceptron, random forest, and convolutional neural network is proposed in these slides. The main area of interest of Mr. Ziming He and Mr. Greg Turk was the Tuolumne River Basin located in California, Sierra Nevada. The region is located in the central location of California inside Yosemite National Park. The O'Shaughnessy Dam, constructed in 1923, and the new Don Pedro Dam, completed in 1971, have been providing water for farmers and San Francisco residents. The area covers the two major origins of the stream flow, Mount Dana and Mount Lyell. Elevation within the area ranges from 3762 meters to 485 meters as the two stream flows down the mountains on the east side of the region to the valleys on the west side. A large part of the region is covered in snow and ice from mid-November to late April, with the heaviest snow coverage centered around months of February and March. The data collection part is comprises of 15 pairs of MODIS versus Landsat. Corresponding pairs were collected from January 1st, 2017 to May 1st, 2017. Bands 1, 4 and 3, which corresponds to red, green, blue channels for MODIS terra surface reflectance, and band 3, 6 for Landsat TOA, which corresponds to green and shortwave infrared channels, were the main focus of this research. So in this slide, we can see the difference between the MODIS's high resolution image and the Landsat's low resolution image. Moving on to the next slide. Data processing. Because of the sinusoidal mapping of MODIS imagery, the images appear to be composed of tilted parallelograms in comparison with Landsat images. For each MODIS image, a flood fill algorithm was utilized to collect information about colors of the same region. Since the amount of pixels in the region can be fairly large, in order to avoid stack overflow problems caused by very deep recursion, an iterative implementation of flood fill algorithm based on Q, also known as the forest fire algorithm, was used. After finding the information for the MODIS grid and corresponding Landsat regions, the data, which was the matrix with condensed information, was fed into the machine learning models. Methods. The ground truth fractional snow snow percentage for a MODIS region is computed based on the normalized difference snow index of the Landsat pixels. This is calculated based on the normalized difference between the green and the mid infrared bands. The normalized difference snow index (NDSI) value is calculated based on the following formula: NDSI equals to B3 minus B6 by B3 plus B6. Here B3 is the green color band and B6 is the shortwave infrared band 1. And we proposed and adjusted NDSI to model the correspondence between MODIS and Landsat NDSI. We then thresholded the NDSI value to estimate the presence of snow. If the NDSI value is within the bound of 0.0 to 1.0 and over the threshold of 0.5, then there is a great probability of snow presence and vice versa. By thresholding each Landsat pixel and summing over all pixels in a MODIS region, we calculated the fractional snow cover percentage for the MODIS region as follows. Snow cover percentage equals to 1 by n summation of 1 to n snow binary, where snow binary is 1 if NDSI pixel is lesser than threshold or 0. N is the total number of Landsat pixels inside the MODIS region. The error between the model outputs and the actual pixel values is calculated based on the mean squared error between observation and predicted values. Now the models used. The experiment was conducted on 3 machine learning models: multilayer perceptron, random forest, regression trees, and fully convolutional neural networks. Mean squared loss for all the 3 models were used to assess the performance of each model. Multilayer perceptrons. Multilayer perceptron has been largely employed in regression problems as it is rather easy to implement and performs well for most of the regression problems. There has also been researches done using neural networks, a collection of perceptrons, to forecast snowfall. In addition, neural networks has also been used to predict snow cover in high altitude. We use multilayer perceptron as a baseline of comparison for our models. We employed a 3-layer fully connected neural network with hidden layers 5 size, 16, 8, 6 and 10 each activation function to model the relationship between color channels and fractional snow cover. Random forest regressors. Random forest regressor is an ensemble learning algorithm that takes advantage of combination of weak learners. Random forest regressors has been used to quantify errors in snow cover datasets. This machine learning technique also performs well for classification problems on MODIS time series data. As the dimension of the input data is fairly small, it is expected that weak learners like random forest to be able to model the relationship fairly well. A random forest regressor comprising of 10 estimators or trees was used in this case. Convolutional neural network. Convolutional neural network has gained its popularity from computer vision tasks such as identifying objects from pictures, recognizing scenes, and segmenting objects in order to take advantage of the neighboring information inherent in satellite imagery. A fully convolutional neural network was used to model the relationship between the neighboring regions. The neural network architecture used in the experiment is shown below with ReLU activation, layers, and mean squared loss. The kernel size are 5 x 5, 3 x 3 with strides 1 and with same padding on the boundary pixels. So we can see below the actual architecture of the convolutional neural network used in the in our experiment. So the result. The data set was divided into 72% training set, 20% testing set, and 8% validation set. Out of the 3 machine learning models, fully convolutional neural network produced the best result with relative low mean squared error. The fully convolutional neural network is able to be trained in relatively short amount of time with the help of GPU parallelism. So in this result, we can see that multilayer perceptron has 0.0371 mean squared error, but has the lowest training time, 44.35 minutes. Random forest regressor has 0.0190 mean squared error with 79.34 training minutes, and fully CNN has 0.0165 mean squared error, the lowest mean squared error, with 69.51 training minutes. So in this slide we can see the predicted and the actual snow covers. The first picture shows the actual snow cover, fractional snow cover from Landsat image. The second picture shows the multi-layer perceptron prediction. The third picture shows the random forest regressor prediction, and the fourth picture shows the convolutional neural network prediction. So what do we propose? We propose an improved infrastructure for predicting snow cover using machine learning techniques such as multilinear perceptrons, random forest regressors, and convolutional neural network instead of relying on periodic low resolution MODIS and DSI for snow cover prediction. Our solution uses machine learning techniques to model the relationship between various channels, RGBs and infrared channels, and fractional snow cover, which is computed over a region of Landsat high resolution composite. The fully convolutional neural network that we propose produces the most accurate model when compared to traditional machine learning techniques used. This model also produces more accurate snow predictions when compared to traditional snow coverage measurements. Conclusion. Due to the high albedo of snow, its presence can often be easily identified from the visible and passive microwave images. Numerous handcrafted retrieval methods tailored towards specific sensors have been developed towards routine products of snow extent, melt, albedo, depth, and water equivalent. Recently, a few studies explored the use of deep learning to extract snow cover from remote sensing imagery and evaluated its potential against conventional methods. For instance, Zia et al. Used a multidimensional deep residual network to classify snow and cloud covered images on multispectral Huangjing-1 satellite imagery over Tibet Nijwan et al. Developed a hybrid method that integrates an AlexNet based deep learning network with Sentinel-2 optical images as the input and a random forest classifier with handcrafted features based on Sentinel-1 SAR and SRTM DEM to extract snow cover in northern India. Validating against ground truth based on field observations, they showed that their hybrid method gave the best accuracy 98.1% and highest kappa coefficient 0.98 compared with the conventional machine learning methods accuracies ranging from 77% to 95%. Guo et al. First trained DeepLab 3 Plus with a 30-meter snow cover product based on Landsat 8 based normalized difference snow index, and then fine-tuned the deep learning network using a smaller amount of training data based on 3.2 meter resolution Graphene 2 imagery. Their initial experiments demonstrated that such a deep learning based model can differentiate snow from clouds despite their similarity in RGB channels and even recognize snow in image shadows. In addition to snow cover, deep learning has also been used to retrieve snow depth. Brackman, Folgman, and Donlon proposed a deep learning based retrieval algorithm for estimating snow depth on Arctic sea ice from passive microwave radiometer measurements. Their input data included 3 AMSRT2 based brightness temperature TB ratios, vertically polarized TB at 18.7 versus at 36.5 gigahertz, vertically polarized TB at 6.9 versus 18.7 gigahertz, and vertically versus horizontally polarized TB at 36.5 gigahertz, plus one SMOS based TB ratio, vertically versus horizontally polarized TB at 1.4 gigahertz. They use snow depth measured from an airborne radar by NASA's Airborne Operation Ice Bridge campaigns to train their DL network that consists of 5 fully connected hidden layers. Comparing with 3 empirical snow depth algorithms, the authors showed that the deep learning based ones give the highest accuracy. They further demonstrated that the deep learning estimated snow depth could improve the retrieval of sea ice thickness when converting altimeter measurements of ice freeboard to sea ice thickness. So this is my presentation. Thank you.